Okay, one announcement before the class. There is a Q&A session for the fourth milestone. Okay, that is scheduled on a Monday, coming Monday. Okay, the due, fourth milestone due. So if you have any questions, please come and ask questions. Okay, room 302, 2 p.m. to 8 p.m. So 6 hours, enough time probably. Okay, let's get started. Today's lecture will be super important for the milestone. So please pay very close attention to the lecture today. Again, fourth milestone is about what? About resolving data hazard, right? So resolving means you need to detect data hazard and fix that problem, right? First detect and fix the problem. Okay, and there are two cases you have to handle, right? This is the first one. If the first instruction is data processing, okay, data processing instruction, this guy is producing this output. Let me do animation. Okay, producing this output, and next instruction is consuming, right? Consuming that. So in this case, simple forwarding can fix the problem, right? Because data addition output is available at the end of ALU, after ALU operation, right? So you can simply forward that data into ALU input. Yeah. If you have video, then please turn on. I can see some of you, so that is going to help me a lot. Okay, thanks, Seijin. Okay, so simple forwarding, right? So you have to be careful. We have only one pipe, this pipe in CPU, right? Think about single cycle CPU design. We have a single unit, instruction fetch unit, single decoding unit, one ALU, memory access unit, okay, module, and write back stage, right? One module. So we have one pipe. So this forwarding means what? You are forwarding ALU output to ALU input, to input, forwarding, right? This forwarding. Okay, so that is the first case. And second case, load use case, right? If the first instruction is memory access, okay, memory read instruction, okay, then and the second instruction is consuming that register, using that register. Then the problem is data, right? Data will be available at the end of memory access stage. After mem stage, the data is available. So simple forwarding, right? That simple forwarding is not fixing that problem, right? Because you cannot use future data. This, if you think of it as present, it's a present now, right? And you cannot use future data now, right? So you cannot. This is impossible. So the thing is, you have to. In this case, you have to. There is no choice. You have to store the pipe decoding stage for one clock cycle. Okay, decoding stage. Bubble means another decoding stage. Decoding stage. Then forward. Okay. So there are two cases, right? First one is this one. Simple forwarding can fix the problem. Second case, you have to store the pipe for one clock cycle, then forward. Store and forward. Okay. So today we will talk in detail how to implement digital logic for that forwarding, and also for store. Okay, so let's talk about this. Okay, so pipeline lecture 2. Okay, pipeline lecture 2. So think about this sequence of instructions. Okay, I color coded orange x2. So first instruction is subtraction. Okay, then subsequent instructions, AND instruction or add, toward, they are using x2 register. Okay, x2 register. So here, pipeline execution diagram. Okay, pipeline execution diagram. So in this case, first instruction is data processing instruction. So you can simply forward, right, that ALU output to ALU input. But you have to be very careful. Here we have a pipeline register. Pipeline register. Okay, this bar, vertical bar, is pipeline register. So big picture first. I'll talk in detail. And how about first instruction and third instruction? We have data dependence, x2, right? So same, situation. You have to. So x2 will be updated in clock cycle number 5, right? But third instruction, that instruction needs that data at the beginning of clock cycle number 5. So meaning, register file is updated, right? Register file is updated here, but third instruction is reading right here, decoding stage, reading from register file. So update here, but read in clock cycle number 4. So one clock earlier, right? So it is, old data, and this is a new data you have to use, right? So it is, passing. The pipe is passing this old data to execution stage. So you are not supposed to use that old data. You have to use your new data, right? This X2, new one, not this old one. This guy is passing. So that means you have to, this forwarding pass, second orange line, first orange line, second orange line, third orange line, right? This second orange line. So this is forwarding pass. Okay. So that means this is a write back stage to execution stage. Here, first one, memory stage, memory access stage to execution stage. Okay, how about this? Dependence between first and false. Okay, addition instruction. Do you have to forward this data to here? So okay, this one. Hijin, can you please read? Hijin. Hijin, you can turn on microphone. No. No. Okay. Singmin, can you please?
Okay, then do we have to do this forwarding? If the write to the register file occurs in the first half of the clock and read occurs in the second half of the clock, then our textbook follows this. If register file writes at the rising edge of the clock, then let's stick to this for our project.
Okay. Okay, think about this. In our convention, in our pipeline convention, remember the shading on the right, shading on the left, shading on the right, shading on the left. Okay, so this is the one. So clock cycle, right? So we have clock running like this. Shading on the right. Shading on the right means here. Shading on the right. Right backstage. Right backstage. Shading on the left. Okay. Right operation. Right operation is happening in the first half of clock cycle. First half, right? First half, second half, right? First half, right? Second half, right? And read operation. Read operation is happening. Read operation is happening at the same in the second half of the clock cycle. Okay, so here the convention shading on the left. Okay, update and shading on the right. So if that is that if we use that convention, you don't have to forward this data to here, because update first, then reading next. So it's okay. You are using your new data, not old data, right? But in our class project is important, right? So we are not using in our class project skeleton code. Skeleton code. Skeleton code. Register file, right? Register file is updated at the rising edge of the clock in the right backstage here. Right backstage. Register file is updated here. The rising edge of the clock, right? Check out our register file design. So at the rising Verilog, at the rising edge of the clock, register file is updated. That means register file is updated at the end, right? Clock cycle 5 here. At the end of clock cycle 5, but fourth instruction is reading from register file at the beginning of clock cycle 5. So update is done in the future, not, so update is done in the future. Okay. So in our class project, you have to create that forwarding path as well. Right. So now, so class project, 3 forwarding paths, 1, 2, 3. Okay, 3 forwarding paths. Okay. So let's talk in detail about this forwarding path each, how to implement that forwarding. Okay, so first take a look at this pipeline execution diagram. So so what do you think? The X2 will be available. Here we have execution stage. That means we have ALU. Here, and then ALU output, right? ALU output is going to be available at the end, almost at the end of this clock cycle. Somewhere, right? Somewhere at this point, right? Time, right? This time. ALU needs some time to compute its output. So almost at the end, at the end of this clock cycle, data will be available. So the thing is, then you can. So there are two different options in forwarding paths. First one, you can forward this data. I'm drawing this very carefully. You can forward this data. You can forward this data to decoding stage. I'm drawing this very carefully. This is clock boundary, right? Clock, right? So this vertical line, that is clock boundary. Okay, or you can forward that data into here. That is design choice, hardware design choice. Which one do you want to use? First one or second one? That means, let me draw a little bit detail structure. Okay. We have, let me focus on, we have a flip-flop, ALU, and then output will be stored in this pipeline register. Clock, these two are sharing clock. Okay, so that guy, okay, so let me draw, separate, flip-flop. Separate flip-flop, DQ, that is providing first source operand, RS1, okay, that is providing second source operand, right? So RS2. So we have register file here. What is it? Supplying that DNQ like this. Let's say ignore immediate, okay, for now, because it is going to be a mess. If I draw immediate sign extension logic and multiplexer and so on, it's going to be a mess, right? So if you implement, if you want to do this forwarding, number one, okay, number one, from execution stage to decoding stage, that means you need to connect. Let me use this one. You need to connect one first. This one. That means ALU output one, right? One. That should be ALU output. That should be. It is going to decoding stage, right? Decoding stage. We have decoding, execution, mem stage, right? So ALU output should be forwarded to decoding stage like this. And also you need to do this, right? This decoding stage, right? Decoding stage. If you want to implement number one, forwarding, right? That means what? That means two candidate to ALU, right? Two candidate to ALU. That means you need to insert multiplexer, right? Simple multiplexer like this. Mux. Okay. 0, 1, and like this, right? You need to insert multiplexer. Mux. Right? Okay. Someone should provide that control signal. Which one you need to select? Mux selection. So that is the hardware schematic for number one, for this number one. Does it make sense? Okay. And number two, what is number two? Number two means, let me remove this. If you want to implement number two, okay, so you don't like this implementation, number one implementation, decide to go with number two. Then number two is what? Number two is mem to execution stage. Memory to execution stage, right? So memory stage to execution, mem to execution. That means here, so ALU output is stored at the rising edge of the clock, right? At this rising edge of the clock, ALU output is stored in this pipeline register, right? Pipeline register, and that data should be forwarded to execution unit like this, right? And then two candidates, right, to one input. So that means you need insert multiplexer here, mux here to multiplexer. like this. Okay, and that that pipeline execution diagram, right? That pipeline execution diagram starts from this pipeline register, okay, and to ALU input. So it is talking about number two choice. Number two, from mem stage to execution stage forwarding. Okay. And also, so let me draw. Okay, okay, I have to use this space very well, but okay. So here, let me try to draw here mem stage and write back stage. Write back stage, and we have data memory, right? Data memory here. Okay, address, right? Address that is going to address, and then this one. Okay, the data you read from this memory, and then we have pipeline register that is separating mem stage to these two stages, right? Mem2, write back. So we have D and Q, clock, same, like this. Okay, so that output. Okay. So to create the second, second pass, second forwarding, that means write back stage to execution. Write back to execution, right? That means what? If I draw, so here, write back stage to execution, right? X2, X2, right? So that pass. So let me remove this. We don't like that. We don't like that, forwarding pass, design choice, right? So we want to go with this, this forwarding, okay? And this forwarding, right? You need to do from write back to execution. So from write back to execution. That means from this point, right? So pipeline register stores the data, okay? Stores the data. So in this case, not the memory data, right? So if I draw more clearly, then here you have ALU output, not the data from memory, right? ALU output should be passed, right? Should be passed to write back stage, T and Q. Here, like this. Okay. Then remember, which one do you want to send? This one or that one? Which one do you want to send to register file, right? So two guys are competing for one input, which is write data. So multiplexer, right? You need getting messy. We need multiplexer that goes to register file. It goes to register file. Okay. So that pass means write back to execution means this one. This one. Write back. This one to. This one to. Here. Okay. Execution. Write back to execution. Also, second source operand, right? To ALU. So write back to ALU. That means three candidates, right? Three candidates are competing for one, input. That means you need to use bigger multiplexer, not 2-to-1 multiplexer. You need to use 4-to-1 mux, right? 0, 1, 2, then 3. We don't use, okay? We don't use the last input. It's okay, right? the last input will be never selected, right? So 4 to 1 multiplexer. Does it make sense? What do you think? Any question about this forwarding? Okay, maybe this one is simple, right? So so you need to, you need to separate stages with flip-flops, right? Pipeline registers, this one, right? Pipeline registers, this one, pipeline registers, this one, this one. Then connect that guy, right? And this guy to ALU input, So right before ALU, you put multiplexer, right? So implementation is pretty simple. And one remaining thing is this selection, right? Selection. This mux selection logic, right? Mux selection logic. So what do you have to do? Control this multiplexer. What do you have to do? What do you think? This mux selection signal to determine data forwarding. Okay, this forwarding and that forwarding. You have to check out data dependence. If second instruction is dependent upon first one, then forwarding, right? And third instruction is dependent upon first one, then forwarding, right? So that means dependence check. How to check dependence? Simple, by comparing destination register number, right, of the first instruction against these two source operand and these two source operand, right? Destination number and source number, right? Destination number, source number. Then when the second question is when here or here, when can you when can you determine that dependence? When can you compare these two register numbers? Can you do it here in clock cycle number 1? No, right? You just read that instruction, right? It has not been decoded. How about clock cycle number 2? Here, can you do that? Not really, because you patch it, right? You read, first instruction. You don't know yet the source operand and second source operand, right? How about clock cycle number 3? Can you do that? Execution, decoding. Yes, you can, right? You can do that, right? Because destination register number, okay? Here actually, so you are passing RD. RD is 2, right? And you just interpreted that second instruction. So RS1 is 2, RS2 is 2 and 5, right? You know that, right? So you can compare these two. Here, right here, in clock cycle number 3. Okay. Then, so it is also design choice. Okay, depending on your design choice, you can compare RD. Okay, RD against RS1, RS2. Okay, so if I draw, some timing diagram, it looks like this. Timing diagram here. RD, right? RD. This is RD in execution stage. Okay, which is 2. EXE, execution stage, right? So you interpreted this machine code in decoding stage, and destination register number should be passed to execution stage until write back stage, because register file should be updated in write back stage. Okay, so you are passing. So here, let me use here the okay. So you are getting instruction. You are getting instruction from instruction patch stage, right? We have D and Q. Okay, so that is instruction. Sorry to be instruction. From here, you can take out RS1. Let's name it RS1 in decoding stage. ID, instruction decoding, right? Decoding stage, and then RS2 in decoding stage. Okay, then that guy should go through this pipeline register. Okay, that guy number D and Q, flip-flop, right? D and Q. So output RS1, let's name it EXE. Okay, RS2 EXE. Okay, so that means here I'm trying to explain how to compare. When do you have to compare, and which signal you have to use, right? So you have to use that signal, okay? And also RD, RD in decoding stage that goes through pipe, okay? And RD EXE. So probably you don't have to forward. You don't have to pass source operand register number to execution stage, right? RD, you should, right? You should, right? So here we have here, right? So then here we have to compare RT and that guy. Destination register number in execution stage. Okay, in execution stage, and RS1 decoding stage, RS2 decoding stage. If I draw here, RS1 2, okay, and 5. Right? So hardware, some hardware unit, some hardware module, let's say forwarding unit, that hardware module should take that guy, this guy, this guy, and compare, right? Compare. Then generate MUX control signal. Control signal. The schematic is going to be messy. Okay. So forwarding, that is generating MUX control. Okay. In Verilog, it is very simple, right? So it is simple combination logic, right? If RDEXE is equal to RS1 ID, then MUX control should be what? Something like that. Which one should be 0 or 1, like this, right? Else, if, something like this, right? In Verilog, right? Like C code. Okay, so that is design choice. You can either compare that guy in clock cycle number 3. Here, clock cycle number 3, Or then what do you have to do? If you generate that control, MUX control signal, right? That is going to be asserted like this. MUX control. Based on this guy, 3 guys, after little delay, this forwarding unit, right? After little delay, it can generate that control signal. So after little delay that signal, MUX control. MUX control signal. This control signal will be generated, right? Then to use that MUX control signal in clock cycle number 4, because forwarding is done here, then you have to use another pipeline register to pass this guy to execution stage, to the next stage, like this, to generate that control signal. Okay, so that guy flip-flopped, okay, pipeline, then you generate this one. So based on this, actually you are controlling this multiplexer. I'm not supposed to, do this. Okay, you need to add one more flip-flop here. One more flip-flop. If you want to use that comparison here. But if you decided to do so it's okay to do that comparison in clock cycle number 4, because forwarding is happening here. Forwarding is happening here. That forwarding, right? That forwarding is happening in clock cycle number 4. So here, probably you want to generate that control signal as well. MUX control signal as well. That means what? That means I want to use instead of this RDEXE, your RDEXE, right? That is going through. RDEXE is going through another pipeline register, and then let's name it RD mem stage. RDEXE, the mem stage. So compare that against right here, RD destination number in mem stage, okay, and against RS1 EXE stage and RS2 EXE stage, 2 source operand in execution stage. Compare these two. That means in hardware you have to pass that guy through this pipeline register. So name it RS1 EXE, RS2 EXE. So compare this guy, okay, RD mem against that guy, these two. So same timing, same clock cycle, you compare destination register and 2 source operand. Does it make sense? So probably you want to take that up, that you want to compare RD and RS1, RS2 in clock cycle number 4, right? And generate that forwarding unit. Forwarding unit receives these 3, okay, RS1, RS2, then generate control signal, okay. Then you don't have to use flip-flop, right? No flip-flop along this line, right? Probably that would be simple. So design choice, okay. So very messy, okay, very messy schematic. Think about that. And the same thing is happening. Same thing is happening here. Second forwarding pass. Okay. to determine that forwarding, okay, to determine the forwarding, let's compare. Let's compare destination register, this one, X2, and to source operand, okay, X6, X2, in this clock cycle number 5. So RT in write back stage and RS1, RS2 in execution stage. Compare these, 2, 3 signals, then generate this MUX selection control signal. Sungmin, after comparison, if RD is equal to RS1, RD goes in instead of RS1. Yes, forwarding path, right, Sungmin, right? If these two are equal, so in this case, in this specific case, RT is equal to what? RS1, right? RT, let's see. Execution, mem, write back. Decoding, execution, mem, write back. Fetch, decoding, execution, mem, write back. So we are comparing, okay, RT, because forwarding is happening here, right? Forwarding from mem stage to execution stage. You want to find out data dependence here as well. Okay, data forwarding, and you have to figure out, do I have to forward this data to here? Make the decision, right? To make the decision, you should compare RT and this guy and these two. Okay, and that comparison, I want to do that comparison here, clock cycle number 4. Okay, so that means, RT in mem stage, RT, which is RT2. Okay, you are forwarding RT, destination register, until write back stage. Okay, which is 2. RT in mem stage, which is 2. Okay, and RS1, RS2. Okay, you know RS1, RS2 in decoding stage, right? And the instruction. And then you are passing RS1, RS2 to execution stage, right? So RS1, EXE, RS2, EXE. Right? So here we have 2, 2, and 5, right? 2 and 5. Compare this against these two guys. So because these two are equal, these two are equal, that this forwarding unit will generate MUX selection signal like this. MUX selection. One MUX selection, ALU input, right? ALU input, MUX selection. Okay, MUX selection. So then multiplexer is selecting then what? That data in mem stage. Okay, data in mem stage. Data in mem stage. 승민. Does it make sense? Okay, then same thing goes to this second orange line, second orange forwarding path. You have to compare RT in write back stage, RD, right? RD in write back stage. X2, 2, right? Against what? RS1, RS2 in execution stage, which is what? 6 and 2 here. 6 and 2. Okay, that is simple forwarding. Okay, that is simple forwarding. Any other questions? And for class project, you have to do this forwarding as well. You know, third, orange, forwarding pass from write back stage to decoding stage. So in our class project, 3 forwarding paths, right? 2 from execution stage, right? 2 from execution stage, 2 execution stage, 2. So first one is mem to execution. Second, mem write back to execution. The last one, write back to decoding. So 3 forwarding passes, sorting paths, right? Okay, then let's move on to, so that is the schematic diagram. Okay, so look at this. Data from write back, mem stage. So that is connected to ALU input through multiplexer. Okay, so this one is connected, this one also connected. So again, mem data in memory stage, mem access stage is connected to execution stage. Okay, then one more. Data from, look at this, follow this line. Data from, I tapped it, right? Tap. Data from write back stage to execution stage. Okay, so multiplexer, right? Then the question is, someone should select one of these three to ALU, one of these three to ALU. Who? This forwarding unit. Forwarding unit is generating this control signal. Okay, then output, right? So what would be input to this forwarding unit, right? So that is the one. So RD, is passed through pipeline registers. Okay, so you tap RD in mem stage, and this one RD destination register number in write back stage. Okay, and then RS1, RS2 in execution stage. Right. So compare these two against these two. Okay, so that is the one. Probably this one is better picture, better schematic, right? Forwarding path from memory access stage to execution. Green, write back stage to execution. And this forwarding unit make a decision, right? Which data should go to ALU, right? The data you read, the red from register file, or red one you got from mem stage, or green one you got from write back stage, right? So okay, that is the one. Think about that. Okay, so then one more important thing, load use case, right? Simple forwarding is not fixing that problem, right? So in this case, first instruction is memory access instruction. Then that forwarding cannot happening, right? So you cannot use future data. Okay. Future data now, right? Present time, right? So you cannot forward this data into here. So the thing should be like thing should be like this, right? So we have decoding stage and stop decoding stage. If you stop decoding stage, then patch stage also stopped, right? You stop decoding stage, then you have one pipe, right? We have one pipe again. Let me remove. Patch, decoding, execution, mem, right back. So you stop decoding, okay, stop. You stop decoding stage, then, okay, don't move, right? Then that guy is also should be stopped. You stop, but this guy is, passing, you're passing this, then it doesn't make sense, right? You're passing this guy, no, it doesn't make sense. Stop it, then you stop the previous stage as well, right? Doesn't make sense, right? To pass the instruction to next stage, right? Then it is overwritten. If you pass, then the instruction in decoding stage will be overwritten. So it doesn't make sense, right? Stop and stop, right? So decoding stage is stopped. Okay. So here, confusing point is mem stage, execution stage, clock cycle number 3. Execution stage is moving. So let me use this. Execution stage is moving to mem stage. Here, that is one. From clock cycle 3 to clock cycle 4. Execution stage, the information, the instruction information, right? Information is passed to mem stage in clock cycle number 4. But decoding, patch, okay, you don't move. Okay, you stop. Okay, you stop. From cycle 3 to 4. Okay, you don't move, right? So that is the final status. Mem stage, right? And decoding stage, then patch stage. The question is, what is this? Okay, so you are moving, then stop. Then what kind of instruction should be in execution stage? So, okay, here in mem stage, you have LW instruction. In decoding stage, you are supposed to have AND instruction because you stopped. And patch stage, it is still reading all instruction. Okay, so we know, okay, mem stage, LW instruction, decoding stage, AND instruction, patch stage, all instruction. And what instruction? What is here? Okay. What would be here in execution stage, right? So what do you think? So let me graphic some animation. Okay, clock cycle number 3. So clock cycle number 3 to clock cycle number 4. Okay, so animation. Clock cycle number 3, you have LW instruction, okay, in execution stage. And AND instruction decoding stage, you are reading instruction, which happens to be OR. Okay, so clock cycle number 4, what should happen is like this. Okay, the instruction is passed, okay, to mem stage. And then, okay, these two guys, okay, don't move, right? But if you don't do anything, that instruction, okay, let me go back, okay? If you don't do anything, that instruction would be passed to execution. So that means it is wrong, right? The original software code is what? Software code LW and OR. Right? If you pass that instruction to execution, you end up executing and the instruction 2 times, right? Doesn't make sense, right? It is wrong, right? So that means you have to what? You have to remove that and the instruction from the pipe. Okay, not 2, just 1 instruction supposed to be executed. So like this, NOP. That should be converted to no operation by hardware. CPU should pass that instruction into NOP. So implementation is very simple. Okay, it sounds pretty complicated, but the thing is super simple, very simple. The question is how to implement, stall, how to stop, right? How to stop these 2 guys. And the question is how to pass no operation, how to create no operation in execution stage, right? The secret is very simple. Secret is pipeline register. We have program counter register. Okay, then instruction memory. Okay, then there is PC, program counter, right? PC, then pipeline register. Okay, then you are passing instruction in decoding stage. So instruction in patch stage. Let me use that convention, patch stage, passing, right? Then register file. Okay, then RS1, RS2 will be passed, right? To execution stage. We have ALU. Okay, that is also passed to mem stage, right? Like this, right? So how to stop the pipe. Secret is again, you play with pipeline register. Okay, that is separating pipe stages. This pipeline register, right? That guy is separating stages, right? Patch stage, decoding stage, execution stage, and so on, right? So secret is, you play with that pipeline register. Okay. So simple thing first. Simple thing. How to make it stop? How to stop that guy and that guy? Simple. We use enabled flip-flop. Instead of this plain flip-flop, we use enabled flip-flop. That one more input, enable. Okay. So it is also, we use enabled flip-flop. So enable means what? Remember, enable the plain flip-flop and enabled flip-flop. If in order to pass, in order to take a picture of this input to output, enable signal supposed to be asserted 1, right? It should be asserted like this. Enable is 1. Then at the rising edge of the clock, okay, enable is 1 at the rising edge. Then flip-flop will store that input to output. But enable is low, 0, deasserted. Enable is 0, right? Enable is 0. This guy is not taking a picture. not taking picture, right? Meaning that what? Meaning what? The instruction in decoding stage will be the same for one more clock cycle. Enable signal is 0, then program counter will not be updated. Same program counter, same memory location will be provided to memory. Then you are reading same instruction, one more clock cycle. So we play with that pipeline register, okay? So by using this enable the flip-flop, you can stop the pipe. Okay, here, enabled, flip-flop, right? Also, here, we play with that flip-flop, enabled flip-flop. Okay. Then one more thing is how to. Okay, so we know how to stop the pipe, right? And second question is how to convert, how to place no operation in execution stage. That is also very simple. We play with control signal. Okay. So what is no operation again? What is no operation? Doing nothing. CPU is not doing anything. No update. Remember, no update. No register file update. No memory update. That means CPU is not doing anything. No operation, right? No update. Just reading. That's okay. Right? But no update, right? You are not updating register file. You are not updating data memory, then CPU hasn't done anything, actually, right? So the secret is, okay, instead of passing this control information, this control unit is generating all control signal. Instead of passing that control signal to execution stage, we are passing what? No operation, the control signal, which is equal to no operation, meaning reg write, we are passing 0 to reg write. Okay, convert reg write to 0 and convert mem write to 0. We are passing 0 to 0 to next stage, like this. Here, by using multiplexer, so look at this. This MUX is receiving two inputs. First one is from control unit. Okay. Second one is 0. 0 means, okay, reg write is 0, mem write is 0, so no update, right? So if load use case happens, then this multiplexer select second input and pass that control signal to next stage, right? Okay, 0. Reg write is 0, mem write is 0. Okay, then the question is, so thing is simple, right? So we know the solution, right? So program counter, okay, we use enabled flip-flop. This pipe we use enabled flip-flop. Then multiplexer to pass no operation. Then the question is, who is generating that enable control signal, and also who is generating that multiplexer control signal? Hazard detection unit, right? Hazard detection unit, right? So okay, let me quickly draw. Okay, so remove first instruction. LW, right? LW X2. Let me use just X2 for X0. So here, patch, decoding. So X2, right? X2 dependence, X2, right? Decoding, execution, mem, right back. So pipeline execution diagram should be like this: patch, decoding, then stop, right? And then execution, memory access, right back. Okay, and then patch, stop. Stop means patch. Stop means decoding, right? Then decoding, execution, mem, and then right back, right? So you have to do this forwarding from here to execution stage. Okay. Then the question is when can you make that forwarding decision? So obviously not here, right? So look at only these two, right? Look at only these two, not here, right? Because you just read that instruction, you don't know X2. You have to compare destination register against RS1, RS2, okay? But you cannot do this here. And can you do this here? Yes, you can do this. You can do that comparison here, right? You know destination register number, okay? Destination register number, and then source register number, right? And you should make that forwarding decision. That decision. You have to make this decision here. If you do that here, then it is too late because you have to stop, right? Stop when you pass. When you pass, you have to before you pass, you have to make that decision, right? So here, you have to make the decision, not here, okay? Because you need to stop. That means RD in execution stage. Look at this. Follow the line. So look at this. Hazard detection unit. Is it receiving? Look at this. Green lines. RD, right? RD in execution stage. RD, right? RD in execution stage. And then RS1, RS2. RS1, RS2 in decoding stage. RS1, RS2 in decoding stage, right? So here, green one. RS1, RS2 in decoding stage. So compare that RT, okay, RT against these two. Okay, then that stop enable or stop control signal will be generated like this. You are comparing RS1, RS2, right? RS1, RTEXE, then RS1, EXE, and so on, right? RS2, EXE. So control signal, after little delay, compare, right? These, three. So signal will be generated like this. This is like stall signal, stall. Right, stall signal, okay? So rising edge of the clock. At the rising edge of the clock, you can take a look at this control signal, right? So flip-flop, right? Flip-flop at the rising edge of the clock, right? At the rising edge of the clock, you can take a look this stall. So enable or stall, right? Stall. So that means, that inverted. It should be inverted. You need to have inverter like this. Inverter, right? Store. Store is asserted. That means going through this inverter, then that is deasserted. Enable is deasserted. So that flip-flop will not store input to output. So again, by comparing this, you can generate this store signal. Store. Okay, that signal also can be used to control this multiplexer. Right. So we have store signal, okay, store, then MUX control. Do I have something? Okay. Okay, that is about milestone number 4. Any question? Before you design digital logic, before you add digital logic, think first. Okay, do not write code, right? First, you have to think first and write code and run simulation. Otherwise, you cannot finish it, right? You just write the code, write the design, add some hardware component, run simulation, then you never figure out what is the problem, right? Think first. Try to draw this schematic diagram. Try to draw schematic diagram on top of the one you drew for the milestone number 2. Right? Milestone number 2 you draw, right? You drew that the schematic diagram of single cycle CPU where there you add flip-flop, okay, flip-flop, then create that path. This path, right? Then by looking at your schematic diagram, then try to figure out the code in Verilog, which place I have to add flip-flop, which I should create that forwarding input, which signal I have to use, that hazard detection, right? This input and that input. Probably that is faster way to finish the milestone, right? So without drawing, without this the rough schematic diagram, maybe it may not be easy to think everything in your brain, right? Okay, any question? Actually, that is about today's class. So better to stop here, right? So next time on Monday, we'll talk about control hazard problem. So 3 kind of hazard, right? Structural hazard. So in our skeleton, we don't have structural hazard problem. Data hazard, force milestone, control hazard, right? So we will talk about control hazard. Probably one lecture would be enough for this control hazard. If you understand data hazard, control hazard is simple. Same principle applies to control hazard. Okay, that is all I have for today. If you don't have any question, we can finish. Okay, see you on Monday, probably in Q&A session, right? If you are confused, probably come to Q&A session and ask questions. Okay. All right. Bye.